So now comes something that most people know from quantum mechanics. The evolution is a linear operator on the state space. In quantum mechanics, this is called unitary evolution. Here it's not unitary, but it shares with quantum mechanics property that's linear. So this is not self-adjoint, but that's not important for this discussion. And whenever you have a symmetry of the dynamics, it means the symmetry commutes with the evolution operator. And we have used it explicitly here. We have either applied the symmetry initial point or a final point. So use it explicitly. So from quantum mechanics, we know that if I can find irreducible representations of the symmetry group itself, the simplest example was the one that did last time. I can decompose all functions that I act on as into symmetric and antisymmetric functions. Then this will be respected by the evolution operator as well. In other words, I can take my evolution operator, which used to be on a big space, Yx, and I can write it as a d by d matrix. So there's a linear transformation, I don't know what to call it, big C and C minus 1. And this is called Clebsch-Gordon, which brings this d by d operator into form of diagonal blocks, and each block is called an irreducible representation, Irreps, and the rest is zero. The simplest example I gave you was for the D1 group, identity and reflection, L Yx can be written as a symmetric combination and antisymmetric combination computed on fundamental domain. So now comes the part that I cannot honestly do without. Okay, so the part that we have so far is totally obvious. We used discrete group to write everything in fundamental domain, and we got some matrices, and they all make sense. There is nothing. The second part is very beautiful, theory of finite groups. So, I've seen lots of exposition. For some reason, there's a book by Tinkham called, I don't know, group theory in quantum mechanics or something like that. It's a little Dover book, very cheap.